Hi, class. So now I would like to talk to you guys about vectors. I'm just going to go back into paper by 53. You guys will see the former lecture there. Um, and I just want to go ahead and close this down. Let me pick a different one here. And let's call this vector. So I definitely plan to share these notes with you. You should see them in folders on Dropbox or in your Moodle shell. So let's talk about vectors, and let's talk about them first. Let's talk about a coordinate system, and I'm trying to think at the same time I'm talking. So we have our coordinate system here, and let's put some tick marks right here. Okay, and let's just say, for the sake of talking, we're going to look at a position along the horizontal direction as well as a position along the vertical direction. Now, normally we refer to these as X for the horizontal and Y for the vertical, but we're not constrained by this thinking. There's no reason why you can't put Y on the horizontal and X on the vertical, as long as you define this, explain this when it comes to talking about things. Just normally, this is the way we define it. Okay, so let's say that we want to put a vector at position 3 here, or unit 3. This vector is going to be, it's going to look like this. But this vector can be defined in terms of an ordered pair. That ordered pair is going to be 3, 0. And ordered pairs look like this: X and Y. That's an ordered pair. But it's an ordered pair in this particular case because those are the dimensions that we're using. Or we can have 30 dimensions on here if we want to. We can put time, we can put the Z direction, we can put temperature, we can put current. I mean, if those are the things that are involved in your discussion, if you're looking at the relationships between those two, hey, you can do that. You can come up with a very complex equation, which is not really that complex at all once you really think about it. So now we have a vector. We've defined this vector. We've defined a position of some object at 3. And we're using this origin to say, oh, this is our 0. So we're starting at the origin, we're measuring from the origin, and we're going out to 3. Now, what's the point in the origin? The point in the origin is that we all agree where we begin. And we all agree for each specific unit. Okay? 1, 2, 3. 1, 2, 3 of what? Meters. If we're all in agreement, then we can all repeat this measurement effectively. You can teach a 3-year-old to repeat it. You can teach a 57-year-old to repeat it. Okay? Or they could teach you. So now that's one vector. Let's define a new vector right here. Now we know that the ordered pair here is 0 for X and 3 for Y. Okay? 0 for 3 and 0 for X and 3 for Y. For the orange vector, we had 3 for X and 0 for Y. It's just letting you know how we're measuring things there. Now, let's see where 3, 3 would be located. 3, 3 is located right here. 3, 3. And it forms a new vector. Now, I could have drawn that a little bit straighter. This is supposed to be a parallelogram, so it should go straight across like so, and then straight up like so. Now, this new vector It's like so. Okay? This is forming the basis for our right triangle. Okay? We could easily move our yellow vector here that's representing what's happening on the y to this location right here. And we end up with a triangle. Okay? We have an x, we have a y, and we have, let's just call this r. Okay? So now we're formally specifying exactly what each of these vectors are going to be. We know that x in this particular case is just 3. We know that y is 3. So what in the world is r? Well, r is going to be calculated using a theorem that some of you may or may not know, and it's called Pythagorean's theorem. And I'm not going to get real deep into how it's derived and all of that, but what I do want to say is that it looks like this. It's going to be r squared equals to x squared plus y squared. Or we can rewrite this as r is just equal to the square root of x squared plus y squared. So we could easily calculate r right now. It's just going to be 3 squared plus 3 squared, which just ends up being the square root of 18. And we know that if we have a perfect square in there, like 9 times 2, 9 times 2 is 18, we could pull that 9 out because 3 times 3 is 9, so we can just say 3 times the square root of 2. So we know what r is going to be. It's just 3 the square root of 2. And we'll use this technique again and again and again. Okay? Now, there are some things that I want to add to that, and it's going to be trigonometric functions and how they're defined. The trigonometric the trigonometric functions are defined with respect to x, y, and r in this particular case, okay? So it depends on how we define our angles. We can put an angle here and call this theta, and we can put an angle here and call this alpha if we want to. We know the angle right here, this happens to be 90 degrees. So it's a right triangle. This is what makes it a right triangle, the fact that it's at 90 degrees. Okay, that x and y are at 90 degrees. So let me just go ahead and start working on a new piece of paper here. And let's draw ourselves a triangle. Let's make it fairly big so we can see it. And this is a right triangle. So we, again, remember that we have ourselves a little block right here. That little block is just indicative that there is that this is a 90-degree angle. Okay? And remember, we defined this as theta. And we're going to define this one as alpha. So now let's define the sine function, the cosine function, and the tangent function. Before I do that, I would definitely like to duplicate this page a couple of times. I think that's too many times. Let me throw this one away. So I have 2 pages. So let's define sine. So sine of the angle under consideration if we're considering theta, is just equal to the opposite side over the hypotenuse. So what's the opposite side? This is our opposite side. And remember, we define that as y. And what is our hypotenuse? Well, our hypotenuse is always the largest side in a triangle. And it's going to always be opposite to the largest angle in the triangle. And remember, we define this as r. So we can easily just say, oh, well, sine of the angle theta equals to y over r. Does that make sense? Let me extend that a little bit. let's say we are looking at the sine of alpha. And don't get tripped up by the Greek symbols. Theta is a Greek symbol. It's, in my mind, it's T, but it's th. You know, and then you have alpha. It's probably something else that I can't pronounce, but I'm just taking theta as the, but it could be theta. You know, it could mean something else. So I don't know the phonetic pronunciation of these things. Hopefully I'm not being redundant. But again, the sine of alpha is going to be the opposite side over the hypotenuse. In this particular case, what's opposite to alpha? What's opposite to alpha in this case is just x. We defined that earlier, okay? And what's the hypotenuse? The hypotenuse is still r. It doesn't change. So now we can define opposite over hypotenuse as x over r. I'm thinking that you guys can pick, y'all picking this up, okay? I want to do the same kind of defining for cosine. So cosine of theta is now equal to the, it's not now equal, but it is equal to the adjacent side over the hypotenuse. We know what the hypotenuse is, it hasn't changed, but the adjacent side to theta is right next to it. That's what adjacent means. So we have x over r, because our hypotenuse still hasn't changed. All right. If we do the cosine of alpha, it's still adjacent over the hypotenuse, and it's going to be equal to, in this particular case, what's right next to it, which is y over our hypotenuse, which is r. Okay, I'm hoping that everybody's flowing with that so far. The next one is going to be, excuse me, tan. Tan of theta is equal to the opposite side to the angle tan, or to the angle theta, not r, but to the angle theta, over the adjacent side to that same angle. So what's opposite, y is, and what's adjacent, x. So that means that tan of theta is just equal to y over x. And of course I want to do tan of alpha. And tan of alpha, again, is opposite over adjacent. Our opposite side is x. Our adjacent side is y. So not to get too pinned down into, oh, it's y over r all the time. No, it's based on which angle you're considering in the triangle. Okay. So from here, I'm just going to go ahead and extend on top of all of these things, and I want to give you guys the secant, cosecant, and cotangent. So we can do that on this side. And I just really want to kind of go fast on this one, and I'm just going to consider the theta for now. So secant of theta is actually 1 over cosine of theta. Okay? Cosecant of theta is 1 over sine of theta. And then, what do we have? We have cotangent of theta is equal to 1 over tangent of theta. There's no need, we're not going to really use these a lot except in one experiment, and then we're going to move on from it. But if you ever encounter it anywhere else, you've at least been introduced to it. Now quickly, let's just go ahead and do the secant of alpha. We know what that's going to be. That's going to be 1 over cosine of alpha. And then the cosecant of alpha, it's just going to be 1 over sine of alpha. And then we're going to have the cotangent of alpha. And we know that this is just 1 over the tangent of alpha. And that's it, okay? These are your notes. You can utilize these. We will refer to this theory when it comes to doing the experiment for the Unit 1 circle, or I keep saying Unit 1 circle, but it's the Unit Circle lab and then the Extending Trigonometry lab. We'll also utilize it for 2 more radii and the the PVC experiment. Okay?